Welcome to SS2 Computer Science, Term 3, Week 13. An operating system, OS, is the most fundamental software running on a computer. It manages hardware resources and provides services for application programs. Process management is one of the OS most important responsibilities. Understanding how an OS manages processes helps you understand why your computer sometimes slows down, how multitasking works, and what happens when a program crashes. By the end of this lesson, you will define a process and distinguish it from a program, describe the process lifecycle and states, explain CPU scheduling algorithms, understand deadlocks, and answer WAEC questions on operating systems and process management. Let us begin. What is an operating system? An operating system is system software that acts as an intermediary between users/applications and the computer hardware. Key functions of an OS: process management, memory management, file system management, device management, I/O, security and access control, user interface, shell/GUI. Major OSes: Windows, Microsoft, macOS, Apple, Linux/Unix or open source, used in servers. Android is Linux-based, Android and iOS, mobile. What is a process? A program is a passive set of instructions stored on disk, the executable file, .exe, .py, etc. A process is an active instance of a program currently being executed in memory. Key distinction: a program is like a recipe written on paper, a process is the actual act of cooking using that recipe. You can have multiple processes from the same program. Chrome has multiple processes, one per tab. You can open Word twice, two word processes sharing the same program. What a process contains: code section, the executable instructions, machine code. Data section, global variables. Heap, dynamically allocated memory, malloc, new. Stack, function call stack, local variables, return addresses. Process control block, PCB, a data structure the OS maintains for each process, containing process ID, PID, process state, program counter, PC, next instruction to execute, CPU registers, memory management information, I/O status. Process versus thread. A thread is a lightweight unit of execution within a process. A process can have multiple threads sharing the same memory space. Multiple threads within a process can run in parallel, used for responsive programs, UI thread plus background worker thread. Process states, the 5-state model, new, the process is being created, resources being allocated by the OS. Ready, the process is loaded in memory and waiting for CPU time, ready to run but currently not running, CPU is busy with another process. Running, the process is currently executing on the CPU. At any instant, only one process can be running per CPU core. Waiting/blocked, the process is waiting for an event, I/O completion, waiting for user input, waiting for a resource, cannot continue even if CPU is available. Terminated, the process has finished execution, OS reclaims its resources. State transitions, new ready, OS admits the new process. Ready running, CPU scheduler selects this process, dispatch. Running ready, CPU time slice expires, preemption, or a higher priority process becomes ready. Running waiting, process requests I/O, e.g. reads a file, or needs to wait for a resource. Waiting ready, the awaited event occurs, I/O completes. Running terminated, process completes or is killed. The process scheduler. The OS has multiple processes in the ready state. The CPU can run only one at a time. The CPU scheduler, also called the short-term scheduler or dispatcher, selects which ready process gets the CPU next, runs very frequently, milliseconds. Goals of scheduling: maximize CPU utilization, keep the CPU busy. Maximize throughput, number of processes completed per unit time. Minimize turnaround time, a time from process creation to completion. Minimize waiting time, time a process spends in the ready queue. Minimize response time, time until first response, important for interactive systems. CPU scheduling algorithms. First come, first served. FCFS processes are scheduled in the order they arrive in the ready queue. Simple, non-preemptive. Problem: convoy effect. A long process at the front delays all shorter processes behind it. Poor average waiting time. Example: processes P1 burst 24 milliseconds, P2 burst 3 milliseconds, P3 burst 3 milliseconds. Arrive in that order. P1 runs for 24 milliseconds, then P2 for 3 milliseconds, then P3 for 3 milliseconds. Waiting time: P1 equals 0, P2 equals 24, P3 equals 27. Average waiting time equals open parenthesis 0 plus 24 plus 27 close parenthesis divided by 3 equals 17 milliseconds. If P2 and P3 had gone fast, average equals open parenthesis 0 plus 3 plus 6 close parenthesis divided by 3 equals 3 milliseconds, much better. Shortest job first. SJF select a process with the shortest CPU burst time next, minimizes average waiting time, provably optimal for minimizing average waiting. Problem: requires knowing the burst time in advance, not always possible, can cause starvation of long processes. Round robin, each process gets a fixed time quantum, time slice, typically 10 to 100 milliseconds. After the time quantum, the process is preempted and put at the back of the ready queue. Fair, good for time-sharing systems, interactive systems. Problem: high context switching overhead if quantum is too small. Priority scheduling. Each process has a priority. Highest priority runs first. Preemptive. Higher priority can interrupt lower or non-preemptive. Problem: starvation. Low priority processes may never run. Solution: aging, gradually increase priority of waiting processes. Multi-level queue scheduling. Ready queue is divided into multiple queues, e.g. system processes, interactive processes, batch processes. Each queue has its own scheduling algorithm. Processes are permanently assigned to a queue. Context switch. When the CPU switches from one process to another, it must save the state, registers, program counter of the current process in its PCB and load the state of the new process. This takes time. Overhead must be minimized. What is a deadlock? A deadlock occurs when two or more processes are permanently blocked, each waiting for a resource held by another, and none can proceed. Classic example: two processes, two resources. Process P1 holds resource R1 and is waiting for resource R2. Process P2 holds resource R2 and is waiting for resource R1. Neither can continue, they wait forever. For necessary conditions for deadlock, Kaufman conditions, all four must hold mutual exclusion. At least one resource can only be used by one process at a time. Hold and wait. A process holds at least one resource and is waiting to acquire more. No preemption. A resource can only be released voluntarily by the process holding it. Circular wait. There is a circular chain of processes, each waiting for a resource held by the next. Deadlock prevention. Ensure at least one Kaufman condition never holds. Deadlock avoidance. Banker's algorithm. The OS checks before allocating a resource whether the allocation will lead to a safe state, one where all processes can eventually finish. Deadlock detection and recovery. Allow deadlocks to occur, detect them, resource allocation graph cycle detection, then recover, terminate one of the deadlocked processes, preempt a resource. Memory management. Brief overview. The OS manages RAM, main memory, to give each process its own address space. Techniques: contiguous allocation, paging, divide memory into fixed-size pages. Virtual memory, use disk space as extension of RAM, allows processes to exceed physical RAM size. WAEC questions: define process, distinguish program from process, describe process states, explain FCFS/ARA scheduling with example, define deadlock, state 4 conditions for deadlock, define context switch. Key points: OS, operating system, manages hardware and provides services. Key functions: process management, memory management, file system, device management, security. Program versus process. Program equals passive instructions on disk, process equals active running instance in memory. Process components: code, data, heap, stack, PCB. Process control block, PCB stores all information about a process, PID, state, PC, registers. 5 process states, new ready running left-right arrow waiting terminated. CPU scheduler, selects which ready process gets the CPU, runs very frequently. Scheduling algorithms, FCFS, order of arrival, convoy effect, SJF, shortest job first, optimal average wait but needs advanced knowledge, round robin, time quantum, fair, preemptive, good for interactive, priority-based, starvation risk, solved by aging. Context switch, saving and loading process state when switching processes, overhead to minimize. Thread, lightweight unit within a process, shares process memory, allows parallel execution. Deadlock, circular waiting for resources, all 4 Kaufman conditions must hold, mutual exclusion, hold and wait, no preemption, circular wait. Deadlock solutions, prevention, avoidance, Banker's algorithm, detection and recovery. WAEC, state OS functions, draw state transition diagram, calculate waiting time for FCFS/R, explain deadlock and its conditions, define terms, PID, PCB, context switch, thread, scheduler.